Get it on pointer. There we go.
You good?
Yeah. Good.
Okay. We'll get started. So it's my pleasure to introduce Professor Erin Buckley, who's going to be who's a guest lecturer here. She is an associate professor in the Department of Biomedical Engineering. That's a joint program between Georgia Tech and Emory University, and she's also part of the Department of Pediatrics at Emory as well. And she, just as a quick background, she did her PhD at UPenn with Arjun Yode, who's really a pioneer and kind of the godfather of correlation spectroscopies for biomedical applications. And so you'll see a bunch of stuff from my slides as well that pay homage to what he's done. And so she did her PhD there in physics, correct?
Mm-hmm.
And then she did a postdoc at Children's Hospital of Pennsylvania in neurology. And then she did a postdoc after that with Mary Angela Franceschini at Massachusetts General Hospital at the Martino Center in radiology. And after that, she then went to become assistant professor at Emory. And she's really been just a wonderful ambassador in terms of diffuse optics and applications for really trying to get things going into the clinic. She uses a lot of stuff that we talked about in the short course, Monte Carlo, obviously the diffuse optics parts, phantom measurements, validation. It's a really nice mix of all these technologies for really important applications. And so with that, I will turn it over to Erin. So let's welcome her.
Oh, well, thank you for such a nice introduction. So yeah, as Bernard mentioned, I have been doing DCS for a long time now. So when I feel like the traditional path for faculty is like they do their PhD in X, and then they do their postdoc in Y, and then they do in their faculty position, they like combine X and Y in some novel way that nobody's thought of before. I didn't do that. I did my PhD in DCS, and then I did my postdoc in DCS, and now my lab does DCS. So yeah, I've been doing this for a while now. Although I was kind of surprised at how long it took me to pull some slides together on the basics of DCS, because I don't get the opportunity to kind of really go into it that much these days. I had to pull up my PhD defense for some of these slides. Anyway, so today I'm going to provide you with a high-level introduction to DCS in the first half of my talk, DCS 101, if you will. And then I'll spend the second half talking to you about how my lab uses DCS in the clinic. Definitely focused more on the application side, where we're looking to study the brain and identify biomarkers of stroke risk. So if at any time you guys have any questions, please feel free to stop me and ask. I've recognized that it's 8:30 in the morning and you guys are pretty saturated probably already. So I'm going to try not to make it too math heavy but just let me know if you want me to go deeper or not as deep on any topic. Okay, so I know you all had a lecture on diffuse optics last week, and you learned about near-infrared spectroscopy, right? No? Oh, I thought that was on this. No. Okay, so that's later. Okay, so I'm your first diffuse optics introduction. Oh, okay. Well, then I should have added some supplies on. Well, this is diffuse optics in a nutshell, this picture of your finger on the phone, right? So how many of you guys know what NIRS and DCS are? Or NIRS? Raise your hand if you've heard of NIRS. Okay, and then DCS? Probably fewer. Okay, so we'll start from the basics. So
we have done kind of electromagnetics
and radiative transport equation. Yeah, exactly. Right. Okay. So yeah, that's what I saw in the slides. Okay. So DCS is a type of what I call diffuse optical spectroscopy that leverages what you're seeing with the picture of the phone, the finger on the phone, right? So if you've ever taken your finger, put in your phone flashlight, you're sending white light in, but your hand glows red. And this is because there's this window of low absorption in the red and near infrared range that allows for really deep penetration of red light. And tissue is also highly scattering, so the light doesn't just go straight through, your finger glows red. So DCS exploits this property, just like near infrared spectroscopy does, which we'll learn about later. But unlike NIRS, so NIRS is used to measure oxygenation and hemoglobin content in the tissue, but DCS is used to measure blood flow directly. So we're looking at dynamics of the tissue. So why do you want to measure blood flow? Well, there's many reasons, but I study the brain, and so I know the most about the importance of blood flow in the brain. Although the brain comprises only 2% of the body's total weight, it is the most metabolically demanding organ in the body, and 20% of the blood supply goes there, where it feeds the most dense and complex vascular network in the body. So despite its like unparalleled complexity, the brain circulation is also the most dynamic. Basically, as different parts of the body activate to rapidly switch tasks, they coordinate vasoconstriction and dilation to alter blood flow at different locations to ensure that blood supply is diverted to the locations that are most metabolically active. And then blood flow can be impaired by cerebrovascular diseases, and that's really where my interest lies in the clinic. Stroke, traumatic brain injury, all sorts of bad things in the brain, Alzheimer's, they all alter blood flow, and they can impact the brain's ability to regulate this complex regulation that the brain is always trying to do. So these blood flow impairments are what causes most times severe consequences, cell death or whatever after brain injury. So there are already several powerful tools for measuring blood flow in the brain and throughout the body. I don't mean to just focus on the brain. Again, that's what I study, so it's going to be skewed to that, but you could say this about many organ systems. So MRI, like arterial spin labeling MRI, there's my mouse. Computed tomography, perfusion, PET. But these tools have drawbacks that leave gaps in our ability to assess vascular health in the brain, particularly in patients who are critically ill or young patients who you can't sit still for an hour-long MRI scan, right? So, plus some of them rely on ionizing radiation or contrast agents, and they're extremely expensive. And because of that, they're also not always very available. So we really need better tools that are able to monitor blood flow in the brain at the bedside or in whatever organ choice of your choosing. Although I will point out that diffuse optics only really works for organ systems that are close to the surface of the tissue, like because light has to be able to diffuse there and then make it back to the tissue surface. Okay, so that brings us to DCS. I'm going to start by telling you how it works at a very high level. So in DCS, what we do is we send in a near-infrared light source with a long coherence length. Its coherence length needs to be much greater than the distance between like the shortest to the longest path length that you detect. So typically we use something like a 5 meter or greater coherence length just to be on the safe side. Although I think even that is overkill. Does anyone here already know DCS? Well, a caveat to people like Bernard, who I know do know DCS. I'm going to tell you about traditional DCS. And yeah.
Maybe helpful for students to know what is coherence, because I think some people may not really know what coherence is.
Sure. So I guess at a high level, I think about it that all the photons are coming out with the same phase, roughly, and that the bandwidth of the frequency that the laser lasers at is very, very narrow. If that, I should put a slide in that. That's a good point. How do you convert bandwidth to length? There's a formula, right? Yeah, no, sorry. I should have had a slide on that. But the point is, when you just like your general LED has very low coherence. Even most lasers have they're highly coherent because they're lasers, but we look for very, very this is a specialized laser with a long coherence length. So we pay about 10K for these lasers with this specification. But I want to point out that what I'm telling you about right now, for the majority of my talk, is what I would call traditional DCS. There are many other variants of DCS now that have developed in the last 5 to 7 years, which is awesome and exciting. But I'm going to focus on the simplest one, the traditional one, and I'll tell you kind of at a high level about some of these other variants. Okay, so because your light's highly coherent, well, this would happen even if it wasn't super coherent, but there's going to be a speckle pattern that forms on the tissue surface, and that speckle pattern is going to be constantly changing because things are moving under your tissue. So it's formed by the superposition of all these multiply scattered light fields that travel along different paths from our light source. And they add constructively and destructively to form a speckle pattern. You can't see it with your eye, but it's there. So what we do in practice is we place a detector some distance R from our source, and we track the intensity of just one of these single speckles over time. So if all of the things that moved in your tissue, like if you weren't measuring tissue, if you were just measuring a phantom that was static, like a big blob of titanium dioxide, so something that has scatters in it, but they're all fixed, they're solid. The intensity of your speckle wouldn't change with time. It would just be flat. It would be like this black flat line. But if the scatters are moving, you're going to see slow fluctuations in intensity. By slow, they're still super fast. But like the order of, nano to microseconds, depending on how fast, what exactly you're measuring. And then as the scatters in your tissue start moving faster, the intensity is going to fluctuate faster. And it just so happens that the main thing that moves and scatters light in your tissue are red blood cells. So the intensity fluctuations that we measure with DCS are driven by red blood cell motion. There's movement of other things as well, but nothing is as fast as the red blood cells. So that's really driving the decorrelation, or by driving these intensity fluctuations that we see. Okay, so to quantify the intensity fluctuations, we compute what's called an intensity correlation function. I heard you guys learned about this a correlation function when you learned about fluorescence correlation spectroscopy. But this formula is like throughout all of my talks. I talk about this function throughout all my talks. So it's just the intensity at time t and position r times the intensity at some time t plus tau, some delay time later, normalize the intensity at time t squared. Okay? And this is what it looks like. These are sample autocorrelation curves, or G2 curves, from an experiment where we had a sensor on the forehead here, and we had the participant inhale a little bit of carbon dioxide, not pure carbon dioxide, that would kill you, but just like 5% CO2. Carbon dioxide is a potent vasodilator. When your body senses it, it's like, I'm dying. I got to improve my blood flow to my brain so I don't die. And so it causes blood flow to increase. So this red curve was taken during room air inhalation, and the blue curve was taken during hypercapnia, where blood flow is increased. And you can see that when blood flow goes up, the curve decorrelates faster the curve is left shifted. And the same would be true if blood flow gets slower, the curve would be right shifted. So the whole point of DCS is to figure out how we can relate the decay rate of the curve to the blood flow in the tissue. So to do that, we use something called correlation diffusion theory to fit our measured autocorrelation curves to simple models and extract an index of blood flow in the underlying tissue. And this is DCS in a nutshell. It's pretty simple. Okay, so diving in just a bit to talk about this correlation diffusion theory that we use to relate our intensity fluctuations to our blood flow index. Just like the radiative transport equation that you guys looked at, did you go from the derivation of the radiative transport equation to the photon diffusion equation? Yeah, okay, perfect. So just like that, you can have a correlation radiative transport equation and derive a correlation diffusion equation. And don't get too overwhelmed by this formula. I know it's early and don't start glazing over it. I'm going to walk you through it and you don't have to like remember this exactly. It's a lot. But the first thing I want you to look at in this equation is that it's a conservation equation for the field autocorrelation function G1. So this autocorrelation function, who's paying attention, what's different? It has a big G, not a little g from my slide before, and it has a number 1 instead of 2. So this is because the formula I showed you on the previous slide is the intensity autocorrelation. This is the field autocorrelation, and it's the unnormalized version. So it's the complex conjugate of the electric field at position r and time t times the complex or times just E, the electric field at some delay time t plus tau. And then if you wanted to do the normalized version, which we would call little g1, you would just normalize that to the electric field at time t squared. Okay, but the problem is like this is our theory, it's g1, and experimentally we measure g2, right? Because it's now some people do measure the electric field, but in general, it's hard to measure fields, it's easier to measure intensity. So we've got our measured intensity autocorrelation function. We have to relate it to this theory that we have for the field autocorrelation function. And to do that, it just so happens that there's a relationship called the Siegert relationship that relates your intensity autocorrelation function to your field autocorrelation function. And it's pretty simple. Your intensity autocorrelation function is just equal to 1 plus this coherence factor beta times your field autocorrelation function squared. And this is, I mean, it's pretty simple math to go from the G1 to G2. So beta, this factor here, is a constant that depends on your source coherence, your detection optics. It can be influenced by ambient light and other external factors. We generally know it a priori, or we know approximately what it should be. But most of the time we go ahead and fit for it in our experimental models or in our data analysis. Okay, so going back to this big equation, like I said, this is just a conservation equation for the field correlation in a given unit volume at position r and time t. I find that very conceptually hard to understand. What does conservation of a field autocorrelation function is, which is why I think it's really nice that we have the photon diffusion equation and the radiative transport equation as our analogy, because that makes a lot more sense. But mathematically, the derivation is very similar. Okay, just basically what it's saying. Yeah.
I just wondered if the less than and greater than brackets mean inner product, or is it?
Oh, this one? Okay, yeah, I didn't really go through all these terms. This one?
Well, no, in the E star E.
Oh, it's the ensemble average. Sorry, I'm like making that seem simpler than it is. Yeah.
Okay,
It's the ensemble
thank you.
average. Yeah. Which generally we use a temporal average, which you can do and if you make certain assumptions. Okay, so yeah, I didn't really go through all these terms. I tried to use, they sent out some standard nomenclature, which was super helpful. So I tried to use their standard nomenclature. But D here is just your diffusion coefficient, nu over 3 mu s prime. Mu A is your absorption coefficient, mu s prime is the reduced scattering coefficient, K is your wave vector, just 2 pi n over lambda. Alpha is probably a new one that you guys haven't heard. That's the percentage of scattering events that occur from moving scatterers. We don't know this value, but I can guess that blood volume in the head is roughly 5%. So if I had to make a guess, I would say it's about 0.05, but that's a parameter we don't know. And then the mean, this bracket delta R squared of tau is the mean squared displacement of your light scatterers at time tau. Okay, so just like breaking this formula down, it's just saying that whatever scatters into the volume, less whatever is lost out of lost in the volume due to absorption, or lost due to scattering out of the volume from this dynamic light scattering that's going to happen from our moving scatterers, has got to be equal to what we put into the system from the source. Okay, so this formula looks intimidating, but it can be easily solved if you know differential equations very well. And the good thing is you guys don't have to know it really well because somebody else did the solution for you, and you can just look it up. So if you know, you have to know the geometry of your system. So this is like the faintest yellow I could have chose for my tissue here. But if we're going to just assume that we have a very simple geometry, a semi-infinite medium, where you've got tissue and air and a source and a detector placed on that tissue air boundary. So then we use something called the method of images to find the solution. This is just like a math trick to solving differential equations. And what you find is that I should have put G1 of R at position R and time tau is proportional to e to the minus kappa R1 over R1 minus e to the minus kappa R2 over R2. So R1 and R2 are the distances to your, so it's, again, this is called the method of images. You have to solve it, you make up an image source that's outside of the medium, and it's confusing, but bottom line is these are just like distances to your source, your real source and your image source. And in the limit where your source detector separation is much greater than the mean free path that a photon travels in between scattering events, so 1 over mu s prime, then this whole formula simplifies down to e to the minus kappa r over r squared, where r is your source detector separation. So much easier. And then kappa, this exponent term here, is equal to the square root of your scattering times your absorption coefficient, plus this term now that has all these components that are related to the dynamic scattering in the tissue. So, like I said, alpha is the fraction of scattering events that occur off of moving scatterers, and the bracket del R squared is the mean square displacement of your scatterers in time tau. Okay, so what is the mean square displacement term? So for all of DCS, where everybody assumes that the mean square displacement is equal to 6 dB tau, where dB is an effective Brownian diffusion coefficient. So who knows what Brownian motion is? Like years ago, Brown looked at a piece of pollen under a microscope and he saw that it jittered. It like made a little random walk, just one little pollen molecule. He was like, how is that? Why does that happen? And it's because the big pollen molecule is getting interacted with by the water molecules and it causes it to jitter. So Brownian motion is basically describing like a random walk process. And this is the formula for the mean square displacement of a random walk process. Now we call our diffusion coefficient, so that's like basically the mean square displacement is linearly proportional to time and with a constant of proportionality d. That is our diffusion coefficient. And for Brownian motion, that D is well defined. Like it depends on the viscosity of the liquid that your particle is suspended in, as well as the particle size and some other factors. But we call it an effective Brownian diffusion coefficient. And why do we do that? Because we know, everybody knows red blood cells in your tissue are not just floating around in water, right? They're like flowing really fast through vessels. So a priori, you would think that the red blood cells would experience random flow, so that the mean square displacement would be equal to their velocity squared times their time squared. But when we started taking experimental data with DCS, we saw time and time again, no matter where we put the sensor on the tissue, that the Brownian motion, the random flow, or the random walk motion fit our data much better. I'm sorry, this like super hard to see, but these dots are the experimental data that we took on a rat tumor, on a pig brain, on your leg, and on an adult brain. And we didn't actually put it on an adult brain, we put it on the surface of the scalp, right? But the dots are the measured data, and the blue data is if we assumed that the mean square displacement was equal to 6 dB tau, and the dotted line was if we assumed the mean square displacement was equal to v squared tau squared. So you can see time and time again, the random flow fits were just crummy fits, but the Brownian motion fit were excellent. And when you looked at the diffusion coefficient that we got when we fit these models, because we fit for the Brownian diffusion coefficient, it was orders of magnitude higher than the Brownian diffusion coefficient that you would expect to get from a red blood cell suspended in just like a fluid, right? So I think the dB for a red blood cell is something like 1 × -13 centimeters squared per second. But the effective Brownian diffusion coefficient that we measure is like 1 × -8 centimeters squared per second. So 5 orders of magnitude higher. So clearly that's not what we're measuring, just a red blood cell jittering in the surface. So empirically we observed this, we're just gonna go with it. And then back in 2016, David Boas and others came up with this theory that what we're actually measuring is the shear-induced diffusion of red blood cells that they experience as they traverse through the microvasculature. So shear-induced diffusion is caused by the displacement of red blood cells perpendicular in this direction to the direction of flow. And it occurs due to hydrodynamic interactions with other particles under shear. It really only occurs in non-spherical particles. So basically, I think of it as like the red blood cells are oblong. They have a different force on them at this side of them than up here. And that causes them to kind of spin and move. And then when they move, they bump into they don't actually touch their hydrodynamic interactions, but they push away other red blood cells. And what happens is they start moving in the lateral direction, not just in the direction parallel to the flow. And it turns out that these lateral displacements actually end up constituting a random walk. And then which could be described as a random walk process with a diffusion coefficient. And then as flow increases and this parabolic shear profile increases, like the slope of it increases, that increases your shear, which increases your shear-induced diffusion that the red blood cells feel. So then it increases the magnitude of the diffusion coefficient. So that's why we think that this diffusion coefficient is proportional to the flow in the vessels. This, to me, is still a theory. It's been shown experimentally when compared to laser Doppler. I think it's laser Doppler, maybe it's laser speckle. But anyway, I think it's a pretty compelling one. But yeah.
Have you tried so you showed before with some of the data from tissues that, this one right here, that Brownian fit seemed to do better, and then I guess with the stuff that Dave Boas has been doing, there's an explanation of why that might be. But if you have you tried doing this like on a phantom with like ordered flow where with spherical type particles and have you tried?
So then
doing
it
two
looks like
fits?
random flow. Yeah.
Okay.
Yeah, we have done that. So we took microspheres, which are spheres by definition, and we flowed them through a microfluidic device. And then you see beautiful, and actually same thing if you use intralipid, which is just like a vat emulsion where they're very spherical in shape, you see random flow. So it is something unique about the flow of blood and the shape of the red blood cells that's causing this. That's a great question.
So looking at the fit of the Brownian, looking at the Brownian fit to the data, it's definitely better than the random flow, but
You're right, it's still not great, right? Like, especially at the tail. So, good eye. So what some people do is they use a Brownian plus a random flow fit. Um, I I don't know if that improves the fit because the model is more accurate or if it's just because you have more degrees of freedom. So then obviously like your fit's going to look better. But I think uh, it is a good, like it probably, the motion probably is, we know it is just intuitively both random flow and or the mean squared displacement has contributions from both the random flow and the diffusion coefficient. It just seems like the diffusion coefficient somehow has a larger order. It dominates the mean squared displacement term, which is weird because it's proportional to tau and mean squared displacement from random flow is proportional to tau squared. You would think it would dominate. We this is like one of the things I like about DCS is there's still some really fundamental basic unanswered questions. But bottom line is we've done a ton of validation studies and we know it works. So okay, I say we know it works. I've been doing this long enough to be like, we know it works. Asterisks, I don't know.
Is
Bernard,
it
you-
possible it's also maybe due to like you have scalp and you have brain, so maybe there's like two contributors to the decorrelation? And so, two very different speeds and maybe that's doing something?
So that what I have seen experimentally is what that generally does is make your curve humpier. So like usually you'll see because the photons that decay the fastest went the longer path lengths because they become decorrelated faster. You could think of it that way. So generally, like if you have two layers with disparate flow, you'll see a steeper decrease and then a shallower decrease reflecting the two layers of flow. Now, sometimes you see, a kind of funny shaped curve, like maybe it decays almost linearly. And I think that has to do with like the combination of the two flow rates. And honestly, this is a theory. I really still believe this is a theory. My lab has been trying to actually measure the shear induced diffusion coefficient because we have these microfluidic platforms and we can visually watch the red blood cell motion and try to track their motion and measure the shear induced diffusion coefficient. And it's not trivial, but I'm still not convinced. But I think it's a good theory in general. Okay, so whatever we assume a mean squared displacement that's proportional to tau. So now we can plug this formula into our kappa. And then we have a theoretical formula for G1, which is a function of your source detector distance and your optical properties. So assuming you know the optical properties of your medium, which oftentimes we do because we do measurements in tandem with NIRS, which I realize you haven't measured, but we haven't learned, but NIRS measures optical properties. We then can fit our measured data to this formula for our unknowns, which are alpha and dB. So we fit for those two parameters. Because they're multiplied together, you can't really parse them out, although there was some work a long time ago by an Italian group that tried. And that's what we're calling our blood flow index. Our blood flow index is just this alpha term, the fraction of scattering events from moving scatterers, times dB, this effective diffusion coefficient. And it has units of centimeters squared per second, which is not the traditional units of blood flow, right? What's the units of blood flow or flow in general? It should be a volume per time, right? But this is an area per unit time. It's more of a flux. Doesn't really make sense, but we've again done a lot of validation studies, and we've shown that this index for blood flow measured is quite well correlated with blood flow measured by other modalities. I'll show you some of those later. Man, I'm sorry, my color choice is poor in this. Okay, so I just want to point out that we can solve this correlation diffusion equation for more complex geometries as well. Certainly, here are just a few, right? You could do a two-layer geometry, say if you wanted to study muscle and you wanted to really account for the influence of the adipose tissue versus the muscle tissue, or in the case of brain, if you wanted to say layer 1 was all like skull and scalp and layer 2 was brain. Or you can go fancier and you can do a 3-layer model and have the top layer be scalp and the middle layer be skull and bottom layer be brain. There are definitely solutions for these fancier models. I put this reference here because Hung-Ting Zhao lists out all these solutions in her paper from a couple years ago. But it's more complicated, right? Because then there's more parameters that you need to know. You have to know the optical properties of your layers. You have to know the thickness of their layers. And so it adds complexity. And I can tell you 95% of DCS publications just assume the semi-infinite model, I would say. I don't know that number for sure, but I'm willing to bet money it's close to 95%. Okay, so here's some DCS data in real life. We had a sensor on the forearm, and we put a blood pressure cuff on the upper arm. And the sensor had a source sector separation of 2.5 centimeters, so we would have enough depth penetration. Oh, I guess I should say, because you guys haven't done NIRS, the rule of thumb is that the depth penetration of DCS, just like NIRS, which you'll learn about, is roughly 1/3 to 1/2 the distance between your source and detector separation. So the farther apart you place from your source from your detector, the deeper on average the photons will have traveled before they've made it back to the tissue surface. That being said, why not just go super far apart, right? At a certain point, you're going to be limited. You're not going to detect any light because the light, so it diffuses out from your source in all directions, and it decays, the intensity decays exponentially as a function of your source sector separation. So you'll see, if you guys start looking into DCS papers, 2.5 centimeters is a pretty standard source sector separation that most people can get usable data. So it balances like depth penetration with still having enough light. So anyway, we put this cuff on the arm, we cuffed to above the systemic blood pressure, so we occluded flow in and out of the arm. We did that for about 2 minutes, and then we release. So on the left, you can see representative curves. So we took data at continuously throughout this protocol at about, I think it was 0.3 hertz. So on the left, you can see the blue curve was taken during the cuff occlusion, and the red curve was one of the curves taken during baseline. And we took these curves every 3 seconds, and then I'm plotting the relative change in the blood flow index that we extracted from these curves as a function of time, just because it's easier. The BFI units are like 1 e⁻⁸, so this is prettier, right? So I normalized to the mean blood flow index to the baseline, and you can see that at around 4 minutes when we cuff the arm, blood flow drops precipitously. It stays there for the 2 minutes of cuff occlusion, and then when we release the cuff, you see this hyperemic recovery or overshoot, and then a return to baseline. And this hyperemic recovery is a well-known phenomenon. Basically, the tissue's like, I gotta get oxygen, like send me as much blood as you can. Okay, so just a quick summary to get everyone back on the same page. The goal of DCS is to determine tissue dynamics and extract an index of blood flow in the tissue. We do this by tracking intensity fluctuations and measuring an intensity autocorrelation function. And then we fit for a blood flow index using the semi-infinite solution to the correlation diffusion equation. Any questions? Okay. So DCS has been now validated pretty extensively, both for brain and muscle applications. Again, I'm talking mostly about them because those are the two main, the easiest organs that are accessible by DCS and have the most, I think, clinical significance. So that's the direction a lot of people have gone. Although I will say people use it to measure head and neck tumors, to measure spinal cord injury. Trying to think what else I've seen people do DCS and not much abdominal stuff because it's hard to tell what you're measuring. But anyway, so I'll highlight a few studies, validation studies in the brain, because the second half of my talk will be on the brain. So this is work comparing in babies, comparing against MRI. You can see a very nice linear relationship between the blood flow index measured with DCS and blood flow measured with MRI. This is in piglet brains against bolus tracking time domain NIRS. So NIRS technically can measure blood flow, but the way it does it is you have to inject an external contrast agent and then you measure the washout of that contrast agent. So it's not like an easy thing to do, but you can do it. And anyway, when you do, you see a nice correlation between the blood flow index measured by DCS and blood flow measured with NIRS. And then this is work I'll show you later in adults against Doppler ultrasound. Measurements of blood flow velocity in the middle cerebral artery against your DCS blood flow index. Sorry, I'm realizing I use a lot of abbreviations. This is cerebral blood flow. My husband's a scientist too, and we met in grad school, and then we talk about our work. Like he worked in Arjun's lab, and he did soft condensed matter, so totally different field than me. But we talked about our work a lot. And when we were postdocs, so we had been together for like 8 years, he was like, what is CBF? And I was like, I say that abbreviation all the time. How do you not know? So anyway, I'm like super cognizant of putting abbreviations up. So CBF is cerebral blood flow. You'll see it many times in my slide because apparently I didn't catch them all. Okay. The other thing that but I should point out, so in children, I think DCS works well. Because why? Because children have thin skulls and scalps. So again, we can't go too far between our source and detector because we're limited by SNR. So with the current distances that are allowable, the thin skull and scalp of the babies allows for sufficient penetration into the brain. But in older patients, these extracerebral contributions are likely non-negligible. I was very surprised when we got this result showing a strong correlation between ultrasound and DCS in adults. This is for the absolute blood flow. Now, if you're looking at relative changes in blood flow, if we make the assumption, yeah.
I guess just for everybody else, can you comment on where these measurements are taken?
Oh, good question. We always put the probe on the forehead. Who knows why? Yeah, there's no hair, right? Hair absorbs light. So unless you're bald or have the world's palest blonde hair or gray hair, we don't get very good signal through hair. DCS is an inherently light-starved technique, which I'll talk about a little later. And so, yeah, hair is an issue. I always think of hair as an issue. I will say when we go to the clinic and we work with really critically ill patients, they're like, just shave it off. They like literally one of our collaborators was like, would you like me to make a scalp incision and you can insert your optodes under the scalp? Like when patients are that thick, hair doesn't become an issue. But we do not put holes in people's scalps and put our optodes under it. We like to tout our non-invasive nature. Anyway, hopefully whoever teaches you about NIRS will talk about the amazing advances that people are making in these head caps that are really good at kind of squeezing the aptodes in between hair follicles. And so I think it's not an insurmountable challenge, but it is something that we generally just avoid in all of our proof of concept studies by putting the sensor on the forehead. And the frontal cortex has lots of good things going on that you want to measure. So it's a win-win. It's the same thing for if you wanted to measure muscle in the arm or the leg, hair can be a challenge, although generally much less so of one. Okay, so the other thing that people have validated DCS against is, can we measure relative changes in blood flow over time? So intuitively, like if we can measure an absolute blood flow, we should be able to measure changes in that blood flow, obviously, except not obviously, surprisingly. So in adults, if you have no change in your scalp or skull blood flow, it's easier to measure changes, right? Because the only thing that's in the brain, because the only thing that's changing in your signal comes from the brain. So people have spent a lot of time, I mean, these are just a handful of validation studies, but showing that we can measure changes in blood flow in the brain with DCS. So typically to do these studies, you'll have like a protocol like the one up here, where you'll have a patient sit still for a while and then do some intervention. In this case, it was carbon dioxide inhalation to increase blood flow. And then this will all be done in an MRI scanner or whatever technique that you're trying to validate against. And you'll take concurrent measurements with DCS during your MRI scan at the baseline condition and then during the intervention condition. And you'll compare the relative change in the DCS data during that MRI scan, those MRI scans, to the relative change in the MRI scan, right? So these are just some in piglet brains, showing a nice correlation between the relative change in blood flow with DCS to the relative change in blood flow with time domain NIRS. This was this was in older kids comparing to MRI. This was in babies comparing to MRI, and this was in piglets comparing to fluorescent microspheres. And there's been more work in adults. I do a lot of work in kids, so a lot of my slides that I had to pull from already had kid validation studies in it. So I don't know. I am puzzled because I look in the MRI literature and there's tons of papers about validation of DCS, but when you look at MRI, there's less. And so we have done, I think, a really remarkable job as a field of proving that what we're measuring is what we think we're measuring. And yet I'm always skeptical because I'm a scientist, right? Okay, so what does the instrumentation look like? This is a picture of one of our very old, like one of the first DCS systems that we had, but we still use a very similar design today in almost all of our works. It consists of a small box that houses our laser and detector, and then a laptop for control. And when we open up the box, this is what you see. Okay, it's pretty messy, despite how simple it is. So we have our lasers. We used to operate at 785 nanometers to be close to the isobestic point where, the absorption of oxy and deoxyhemoglobin are the same. But now my lab does everything at 852 nanometers because we do simultaneous monitoring with NIRS and DCS, and we wanted to work outside of the NIRS wavelength range, which we use NIRS wavelengths of 690 to 830. So by working at 852, we can operate everything simultaneously. This had two lasers because we were doing bilateral monitoring, one laser for each side, but you don't need two lasers. Then we have detectors. So our system uses single photon counting detectors because we want to count and time photon arrivals to derive that correlation function, right? We generally use 8 detectors. So we have 2 4-channel arrays of detectors because DCS is inherently light-starved. We have to catch a single speckle, so we use very, very small fibers, like 5 microns in diameter. So we're not getting enough light or a lot of light, and we're trying to count our photons. So because of that, very, very light-starved. So we usually put in 8 detectors, and then we average across all of them to increase our SNR. And then finally, in this box, because this was an old one, we had a hardware correlator board that estimates the intensity autocorrelation function based on the photon arrival times from the detectors. This is now obsolete. We do everything now via software correlation, but overall, the system is extremely simple. It's very plug and play. You just need the right components and plug them together, and it works. There have been several recent advances in DCS hardware aimed at augmenting the depth penetration. So if we typically do a 2.5 centimeter separation, that's roughly a 1 centimeter penetration depth. That's not enough for somebody with a thick head like me to get down to the brain. So people have been very clever in the new techniques that they have. And I just want to give a shout out to Mitchell Robinson, who's at MGH. He made the slides that you're going to see next. And I thought they were so nice. So I emailed him before this. I was like, could I please present those slides? They'll be better than what I do. I did edit them a bit, so they're more comprehensive. So if anything looks wrong, it's probably a part that I edited quickly. Okay. So one thing to improve this, the light-starved nature of DCS that people have done is they've just moved up to work at 1064 nanometers. So we typically work in the near infrared, but there's a second optical window up around 1064. And there, the effective attenuation coefficient, so mu A times mu S prime, is much lower. It's not much lower, actually. It's like 20% lower than in the near infrared. But the other advantage is we are beholden to safety standards because we don't want to burn our patients when we send the light in, right? And the safety standards at 1064 are much, is it lower or higher? You can send in more light and not burn somebody at 1064. So it does enhance your depth penetration, and they've published work at 3.5 centimeters, which is a whole centimeter, almost 50% greater than traditional DCS. The downside is these are like insanely expensive detectors. Another thing that people are doing is incorporating high density spat arrays for parallelized detection of DCS over thousands of detectors. So you can catch thousands of speckles at once. Brilliant, right? In theory, that would increase our SNR by a factor of the square root of the number of detectors. Which is a huge improvement. But in reality, unfortunately, with the spat arrays that are available now, they just don't have quite the time resolution or the detection efficiency to really make it a drastic improvement over current DCS. But I think it's got a lot of promise. I think this is one way that will really advance the field. There's also been the advent of time domain DCS. Unfortunately, you guys haven't learned NIRS yet, but there's continuous wave NIRS where you send in just like, or there's continuous wave DCS, right? Where we just send in a continuous pulse of our laser, or not pulse, just a continuous light beam. We're not pulsing it in any way, but with time domain DCS, if you pulse the laser, you can then, the beam will spread over time at the detector, and you can isolate photons that have arrived at late times to, which effectively means that they have longer path lengths. And so you're isolating those deeper penetrating photons and effectively minimizing the influence of your extracerebral layers that way. SCOS is another technique that has been used. So SCOS is a little different than DCS. With DCS, we're looking at temporal fluctuations in intensity. SCOS looks at spatial variations in intensity. So it takes an image of the speckles and it looks at how the speckles blur, which tells you about the flow in the underlying tissue. It is a very clever technique, and right now people can also get like 3.5 centimeter detection with SCOS. The thing I like about SCOS is it just uses a camera detection, so it's much more scalable than traditional DCS. And then people have also been working with interferometric techniques. These techniques basically split off a little bit of your source as a reference arm. The rest of it goes to your sensor. And then they compare the detected light to the reference arm via interferometry. And what that does is it allows the use of non-photon counting detectors, right? Because now your detected signal is much, the orders of magnitude greater than the single photons that we were detected. So again, it's generally going to be more scalable than the photon counting detectors we use with DCS. Okay, so in practice, this is what our current DCS device looks like. It's got our DCS box, and then we always do NIRS with it. So we do frequency domain NIRS because the two components provide complementary information. So NIRS is getting you oxygenation, hemoglobin content, as well as the optical properties, which are parameters. If you remember the equation that we talked about, you need to know the optical properties of the tissue. So we do the two in tandem, and then you can see the instruments on wheels, so we can wheel it all over the hospital. This instrument is a bit bulky, but the patient interface is just a small optical sensor with a light, well, with a light source and detectors. We tailor the sensors for the application, so we do some measurements where we just briefly hold the sensor over the forehead for some spot measurements that we could track days to weeks. And then we do some longitudinal monitoring where we strap the sensor onto the patient's head for continuous, 2 hours of monitoring. My laser pointer is it looks like it's coming out of the probe. Okay, so further, one of the things about DCS is we aren't just limited to measurements in humans. We can also make measurements in animals non-invasively. We just shrink down our source detector separation. We showed, I don't think I have it, maybe in this paper, that we can go as small as 3 millimeters and all this diffusion approximation still holds. My lab actually has a whole preclinical side where we do a lot of measurements in mice, looking at mechanisms that drive changes in cerebral blood flow after injury, but I'm not going to talk about that today. Okay, so now that you've seen the system and how it works, you can see there's lots of opportunities from it, right? So it's non-invasive. We don't have to put anything into the brain, even if our neurosurgeon collaborators are like, go ahead and do it. We don't do that. It's all non-invasive. And we don't need to use anesthesia. So as long as the patient can sit still for 3 to 5 seconds, we can get a usable signal. So it's great for infant populations like this one, who you can't exactly be like, hold still now. Second, unlike PET or SPECT or CT, it doesn't involve the exposure to ionizing radiation. It's really no more light than you would get on a sunny day outside, as long as you stick to the safety limits, which everybody is tempted to go over because we are so light starved. But anyway, we're also portable, so we can bring our device to the bedside as opposed to MRI or CT, where the patient has to go to the scanner, which is really difficult when you're trying to study patients who are very critically ill, like this guy over here, who are hooked up to all these tubes and wires, and it really makes transportation difficult. And our sensors are small, so they just take up a little bit of space on the head. Like you can see with babies, sometimes you have very little real estate to work with. So having just this small sensor to slip in there is a great attribute. We can also take data with high temporal resolution. So we go up to 50 hertz right now. I mean, the faster you go, the noisier signal is going to get. But the great thing about going fast is that you can resolve things like cardiac pulsatility, which is really important because cardiac pulsatility, the shape of that cardiac waveform changes with things like vascular resistance and compliance. So it can tell you a lot about what's going on in your blood vessels in the brain. And then we can also capture dynamic events like this one. So we can do functional measurements. This is like a finger tapping, this is a super old finger tapping experiment where you can see when the participants started tapping their finger, we see a big increase in blood flow and then a return when they stop tapping. And then finally, unlike techniques like Doppler ultrasound or magnetic resonance angiography, which are sensitive to large feeding arteries in the brain, DCS and NIRS, like diffuse optics in general, are more sensitive to the microvasculature. So the kind of dogma that is that photons that make it to an artery that has a ton of blood and blood is highly absorbing are just much less likely to make it back out to the tissue surface, whereas photons that interact with these smaller vessels have a greater chance of making it back. So that's why we say we're sensitive to the microvasculature. And that's great, right? Because that's where the oxygen exchange is happening, and it's a much more direct measure of tissue health. Okay, but I just full disclaimer, diffuse optics, DCS is not the end all be all imaging modality. This is not DCS. This is MRI. We are never going to get these beautiful whole brain images of blood flow because we have low spatial resolution. And oh my God, that's my phone. I'm so sorry. And we also have no access to structural information. We're always going to be limited to studying regions of the tissue that are closer to the surface of the head. But I really see DCS as a complementary tool to the many neuromonitoring modalities that are out there. You know, maybe you have a DCS tool that you can monitor continuously at the bedside, and then when things start looking different or weird, then you send the patient to get their MRI. Okay, so I've covered the basics, and the last like 20 minutes, I thought I'd show you just a couple of examples of how we use DCS in the clinic. I can kind of whip through this. Yeah, do you have? Yeah, absolutely.
Remember that slide where you compare your different wavelengths, like the 850 and the 1060?
Yeah.
Can you talk more about what you're seeing in these publications that y'all did with the 1064 pulsed laser versus not pulsed? Like what differences you
yeah,
see
sorry.
in your data?
I shouldn't. So again, this slide was for Mitchell Robinson. So he was doing something fancy with his 1064 pulse laser. Just in general, you can use any wavelength for the time domain system. But the idea is that because you're pulsing your laser and then the light that gets detected will have a spread because the photons have traveled, like they're not going to look like that sharp pulse anymore. They're going to spread. Because photons have gone all different path lengths to reach your detector. And then you can pick the photons at the end of the tail and look at the correlation from those long photons. Now you can do this at 785 or 850 nanometers. You can also do it all the way out at 1064, which is even better because then you have further enhanced penetration. Does that kind of get at the
Yeah,
answer
I
to your
was just
question?
curious because our lab, we do photoacoustic imaging,
Yeah.
and we've been exploring the NIR2 region, and 1064 is a wavelength that
Yeah, absolutely.
we've been experimenting with. But I feel like it's still kind of a new
Absolutely. I
a
mean,
new area. So I was just curious, like if y'all saw benefit in your data by using that wavelength, because
Yes.
that's not a common wavelength to choose.
they definitely do. I should say I did not publish these papers. This is from the group up in Boston. Nobody else can do it though, because the detectors are like $200,000.
Yeah.
So, and they're like made by Lincoln Labs and they're super fancy. So yes, I think it is a very promising approach and we should work towards that. But right now it is not a tractable
For the DCS
solution
detector,
for people at the moment. But I don't know. I talked to some people at Lincoln Labs. They are trying to commercialize their product and scale it up so they can get the cost down. So, you know, maybe in the coming years or maybe some innovative young minds who have some ideas on how to make the detector capabilities at that wavelength better.
What is the distance between the
Oh yeah, so for time domain DCS, the nice thing is you can use short separations because you can isolate the photons that have traveled long distances more easily. So they don't need to do a 3.5 centimeter separation measurement to still get that same level of depth penetration. Good question. Which is nice because then they get more light, right? Yeah.
small, like
This is just small, but like how much movement can you have while taking data? Because like MRI is so confining and claustrophobic. So if, especially I know for children who are like autistic or in the spectrum, like it's really hard to study their brain specifically because it's nearly impossible to keep them 1 hour just like sitting still. So do you know if like this has been used to also study a little bit more about how their brain behaves differently or if it does at all, even
So
while they're moving?
that's a great question. So motion artifact is an issue with DCS depending on how long you, like right now, what we do is we acquire autocorrelation curves at mm, I don't remember exactly how fast, something like 1 millisecond. And then we average multiple curves because this SNR is really bad in 1 millisecond. Then we average multiple curves to come up with a cleaner curve at the end. So if you average for 50 milliseconds, as long as the patient's still within that 50 millisecond time, you're good, right? And then if you want to average like that arm data I showed you, we were doing 0.3 hertz, they have to be still for 3 seconds at a time. Now the challenge comes in if you're doing continuous monitoring and the patient all of a sudden, you know, scratches their forehead and moves the probe a little bit, or when they move, the probe moves, and then you're probing a slightly different region, and then it's hard to say, well, was that movement artifact and we can just remove it, or did the probe move? And so I think motion artifact is definitely a challenge with DCS when you're doing the long-term monitoring. But I think by adding accelerometers to your probe and working on better, or to your, I try to call them a sensor, not a probe, because probe sounds super invasive. But by adding accelerometers, you can sense when the patients are moving. And then also working on ways to really secure the probe so it doesn't move during movement. I think it's a not a huge challenge. I will say though, like I always am nervous whenever we see spikes in our data. Is that motion or is it real? Especially when like autistic kids, you can probably attribute it to motion, but in patients in the ICU, sometimes they have little events that like could cause changes in cerebral hemodynamics. So we always kind of take a holistic view. We look at what happened to their heart rate during that time, their blood pressure and all that. And then we say like, do we think that was a motion artifact or was it a real event? It's a nuance to our analysis that is not often talked about. Some of these techniques are more sensitive to motion than others. The interferometry technique, my experience has been that it's been highly sensitive to motion, although they have the group that really has pioneered it, Vivek Srinivasan's group, they have some amazing videos of people moving all over and they don't see changes. So I gotta figure out how they do that because anyway. Okay. Any other questions? Okay. And I have how much time left? Like 20 minutes? It ends at 10? Okay. So I'll start by talking about subarachnoid hemorrhage. So subarachnoid hemorrhage, for those of you who don't know, is just a devastating type of stroke where you have a ruptured blood vessel in the brain that leads to blood in the subarachnoid space around the brain, which is bad. It causes pressure and it will kill you if they don't drain the blood and fix the rupture. It's associated with roughly 20% in-hospital mortality and substantial morbidity, with like almost half of the survivors being unable to return to their pre-occupation illness. So, or pre-illness occupation. So what a common complication after SAH is called cerebrovascular, and what happens is that the blood vessels aberrantly constrict, right? They're not supposed to constrict, they just do, probably due to all sorts of toxic things that have been released into their brain. And this is bad because it limits blood flow. And in the worst case, it leads to secondary stroke called delayed cerebral ischemia. And Delayed cerebral ischemia is associated with even worse functional outcome and quality of life. And there's really no proven method for predicting who's going to spasm or who's going to develop DCI. So tools that can track this evolution and predict vasospasm or DCI could be really useful to let clinicians know they need to change their treatment strategies. So given that blood flow is a pathway that's affected by this disease, and we have a tool that can measure blood flow, we wanted to look into the utility of this tool to address this clinical need. So as a low-hanging fruit first experiment, one of the first things we did was look at the cerebral hemodynamic effects of the main treatment that our collaborators at Emory use to treat vasospasm. So what they do is they give intrathecal nicardipine. Nicardipine is a calcium channel blocker that acts on vascular smooth muscle cells to dilate the blood vessels and restore perfusion. And they give it intrathecally, so into the ventricular space, because these patients have a ventricular shunt to drain the blood already that was in their brain. So they've already got a shunt, they've already got access. They give it intrathecally with the idea being that the vasodilatory effects of the drug will be limited to the brain, because you don't want vasodilation systemically in these patients because that's going to reduce their blood pressure and could also reduce blood flow to their brain. So our collaborators at Emory have already looked at the macrovascular effects with ultrasound of this treatment, and they've confirmed that it does induce vasodilation. But we wanted to look at the effects of microvascular blood flow because while intuitively you'd assume that there would be similar effects because your arterial and capillary bed is governed by similar calcium-dependent processes. There's no guarantee that this intrathecal delivery will allow the drug to diffuse into the out of the subarachnoid space and reach the smaller blood vessels in the brain. So we use DCS to answer this question. Basically what happens is the patient comes in with an SAH. Once vasospasm is detected, they start treating with nicardipine every 8 hours for roughly 2 weeks. And then, sometime later they're discharged. And in the meantime, they're getting CT images to look for that delayed cerebral ischemia that I was telling you about. We focused on the first 3 doses of nicardipine that were given to monitor the blood flow response to. And for these measurements, like Bernard said, we put the probe on the forehead. This is a super old version of our probe. And we monitored the blood flow response for up to 90 minutes after the drug was given. These patients also get daily assessment with ultrasound to look at the blood flow velocities in their large feeding arteries of the brain. So one of the first things we did was compare DCS to ultrasound because, like I said, there's been tons of validation, but I'm always skeptical. I'm always like, does it work? I got to check. So we had the opportunity to check. And we did see a strong positive correlation between ultrasound and optics, giving us confidence that the semi-infinite model that we're using in adults seems to be valid. So next we looked at the effects of the drug. So here I'm plotting the relative change in blood flow, or this blood flow index that we measure as a function of time post-administration of the drug. This was in 20 patients on the first day of treatment. You can see that flow significantly increased due to nicardipine. On day 2, we saw similar levels of increase. And then by day 3, the results are a little bit more blunted, which agrees with some pharmacokinetic data that they've taken looking at the concentration of the drug in this CSF. But what was interesting is that when we looked that what I was showing you here is the mean response across all our patients. But when we looked on an individual level, the responses were quite heterogeneous. There were some patients who actually decreased, this patient was crazy, but they were all over the place. So we wanted to better understand what could explain the heterogeneity in their response. So we used this thing called a latent class mixture model. That's a way to kind of objectively identify classes of more similar responses. And this model classified our data into 2 similar response classes. It couldn't classify this blue guy. But all the people in green were the people who saw an increase a steady increase in blood flow after the drug went in, and all the people in magenta were the group of minimal responders. And then we wanted to better understand what was unique about the patients who fell into these categories. And we looked at a few parameters like changes in blood pressure or the severity of their injury, or the changes in their intracranial pressure. And what was most striking is that there was a big difference in the incidence of delayed cerebral ischemia, so that secondary stroke that they get, between the two response classes, where all the patients who had minimal response to the drug ended up developing delayed cerebral ischemia, whereas only 1 out of the 13 patients in class 2 developed the injury. So this data was published back in 2023. And we use this data to power a larger data set, and which we're still ongoing, but we've now enrolled 47 patients, 12 of whom have developed the secondary stroke, delayed cerebral ischemia, and 35 who didn't. And we used a linear mixed effects model with CBF on time in the presence or absence of this injury. And the results show that on day 1, there are still significant differences between the patients who don't develop secondary stroke versus those who do. These differences are gone on the 2nd and 3rd day of treatment. But we're excited because our preliminary results seems to be holding up as we increase our patient numbers, and they suggest that DCS could be used as a powerful biomarker of outcome after SAH, where if flow fails to respond to the treatment on the first day, it could alert clinicians, treatment's not working, try something else. So we're still increasing our numbers, and we hope to publish our larger study soon. Okay, so and then my last application is in sickle cell disease. So like I said, I work a lot in kids. So this is working kids with sickle cell disease. Sickle cell disease is a blood disorder that has a profound effect on all organs in your body because their mutation in their hemoglobin causes sickling as well as altered red blood cell morphology and rheology. And it leads to insufficient oxygen delivery to the tissue and vessel occlusion as well, because the red blood cells are sticky and they stick together and block the arteries. So as an effect, the kids have a high risk of stroke. About 2 to 10 of them will have 10% of them will have an overt stroke by the age of 15, I want to say, where that's like one of those massive strokes that you think of when I say stroke, where they've got like loss of limb function or facial drooping. But about half of these kids will have something called silent cerebral infarcts. These are clinically silent, but you can see them on neuroimaging scans, and they're associated with lower IQ and worse school performance and all that. So they're bad still. And the mechanism of stroke in these kids, although it's a little unknown, one mechanism just arises from the presence of chronic anemia, right? So these kids, their cells lyse very fast. And so they're always anemic. And as their anemia worsens and their oxygen content in their arteries is decreased, what happens is to compensate so that oxygen metabolism can meet metabolic demand, blood flow starts going up. Their blood vessels start dilating. And then at a certain point, they can't dilate more, as the vascular reserve is exhausted, and then they start taking more oxygen from the tissue, from the blood vessels to preserve metabolism. But then they're in this state of limited or no reserve, and they're vulnerable and ill-equipped to handle an increase in metabolic demand. Like, for example, if a patient gets a fever or an infection, and there's eventually going to be a mismatch between, what they need and what they're getting, and stroke ensues. So we can assess these parameters. We can get blood flow from DCS and oxygen extraction fraction from NIRS. And then when I didn't add slides about this, but another perk of DCS is when you combine blood flow from DCS with oxygenation from NIRS, you can estimate oxygen metabolism, which is a great parameter. Like, that's how much oxygen your tissue's metabolizing. That's really important in a lot of disease states. Okay, and as I told you, like the existing neuromonitoring tools to measure these parameters don't cut it, but DCS and NIRS do. So we've done a lot with DCS and NIRS in these stroke kids, or sickle cell kids. I won't tell you about this. We quantified the repeatability of our measurements, which was pretty good. We validated it in kids with sickle cell disease. So one of the big things about sickle cell disease is it changes the concentration and the shape of your red blood cells. So we wanted to understand how that affected our DCS signal and confirm that DCS could still work in these kids. It does seem to correlate well with arterial spin-labeled MRI, which is a way with MRI to measure blood flow. And it also correlates well with ultrasound, which is another way to measure blood flow in the large arteries. I don't know if I need to go into this, but another thing that can affect the blood flow index is hematocrit. So what's the definition of hematocrit? How much blood per, or how many blood cells per unit blood that you have, right? That intuitively will affect the shear-induced diffusion, right? That we think we're measuring. So the more blood cells you have to bump into, the more your shear-induced diffusion. So we wanted to look in, there's been all these methods proposed on how to correct DCS for hematocrit, and we used all of them, and honestly, it didn't seem to matter. No matter what we did, we still saw a strong correlation between our optical measurements and ultrasound. So we were encouraged by that. So then we've done a lot just showing that DCS is sensitive to alterations in cerebral hemodynamics in sickle cell disease. So this is our blood flow index in kids with sickle cell versus control. They have elevated blood flow, like I said, and we were able to see that. We also saw an inverse relationship between how anemic they are, how much hemoglobin they have in their blood, to their blood flow. So the more anemic they are, the higher their blood flow. How much time? Okay, I still have 10 minutes. We've also been exploring ways to look at vascular reactivity in these patients. So basically, in a lot of diseases, what happens is that mechanism, like I mentioned at the very beginning of my talk, that mechanism to control constriction and dilation and divert blood flow where it should be going gets damaged. And so it's very powerful to have a marker of how damaged it is. Like you could have a patient with a very normal blood flow, but they have no capability to change that blood flow, like if their blood pressure drops, right? So you want to know how reactive their vessels are. And that's something that DCS can provide. So to do this, we had the participants just hold their breath. Holding your breath increases your carbon dioxide content to your blood, and so it should increase blood flow to the brain. And what we found is that in kids with sickle cell disease, they have significantly worse vascular reactivity than in their healthy control counterparts. So all of these findings aren't really novel per se. They've been shown by MRI, but we can see them with DCS, right? Which is exciting because DCS can, in theory, if it were commercialized and made readily available in hospitals, could be used in the outpatient clinic setting to assess these parameters and give clinicians a better picture of the brain health of these kids so that if needed, we could initiate, better treatment strategies earlier. We've also been using diffuse optics or DCS to assess the influence of therapeutic strategies that are aimed at improving anemia and mitigating stroke risk in these kids. So the most established is blood transfusion, which is the standard practice for kids who are at high risk of stroke. And basically what it does is it increases your arterial oxygen content, and therefore it shifts the brain from this more vulnerable state to a less vulnerable one by and relieves metabolic stress. So we monitored a bunch of transfusion events in kids with sickle cell disease, putting the sensor on their forehead. We saw the expected decreases in oxygen extraction fraction measured by NIRS and blood flow measured by DCS, which was great. And expected. But one of the things that we've been looking at lately is like you can see some kids had an increase in blood flow, and we were like, what's going on with that? And so we started looking a little closer. And we had this hypothesis that perhaps the presence of large vessel vasculopathy could explain some of the disparate response. So one of the reasons patients go on transfusion is because they have evidence of vasculopathy, which is basically like your blood vessel, your large beating arteries that should be large and open to allow a lot of blood, they start closing, which is not good. You can see evidence of the narrowing on a magnetic resonance angiography. And so transfusion therapy can help slow the progression of vasculopathy. So a lot of these kids were on it for vasculopathy. And what we found was really interesting, although it's a little hard to explain, but basically what we saw was that we dichotomized their blood flow response to transfusion into 3 groups. So on the y-axis is how much their blood flow changed, where 0 would be no change. And all the patients without vasculopathy, except for this one who I just learned actually had vasculopathy when we dug a little more, but everybody who didn't have vasculopathy had a decrease in blood flow, which is what we expect them to do on transfusion therapy. All the patients who had vasculopathy, almost all of them, had an increase in blood flow, this paradoxical increase. It's almost like they were maybe low to begin with, and so giving them transfusion helped them increase their blood flow to their brain. And then we tracked these kids with MRI for 2 years later, and there was a small group of kids who were no to start, but they developed vasculopathy after a transfusion. And you can see that even before the vasculopathy was diagnosed on MRI imaging or MRA imaging, that you could their blood flow response to transfusion was different. So it suggests that maybe the DCS measurements of the response to transfusion could provide early warning signs of that transfusion isn't maybe working as well as they want it to, and they need to increase the rate of transfusion or give more transfusion or add on secondary treatments to mitigate the progressive worsening of vasculopathy. Okay, I'm going to stop at that and just say that our ultimate vision is that just like we have glucose monitors for diabetes, we could have DCS blood flow monitors in the brain for kids with sickle cell disease. They could be, you know, just hanging out at home, check their blood flow, see how they're doing that day. If it's too high or too low, they can get to the doctor and initiate treatments sooner to avoid stroke and other bad things happening to them. And with that, I'm going to end here and thank you guys all for your attention. You're very kind.
Any questions for her?
I had a question. So at the beginning of your talk, you talked about how when you're doing the autocorrelation fitting, how it matched better with Brownian motion because of like the shape of red blood cells. Do you see like a difference in that with sickle cell?
Yeah, that's a great question. That is really hard to test. So what we are doing to test that now, like it looks normal if we just look at the data. It still fits the Brownian motion model, but it's hard to compare apples to apples. Like if I had, because they're anemic too. So if I had two, like a sickle patient and a healthy patient who had the same blood level, like would I see the same blood flow? So instead, what we're doing, we have these microfluidic phantoms that we made, and we are getting blood samples from kids with sickle cell disease and normal blood donors and flowing blood through them and trying to figure it out. I will say though, I'm not a hematologist and I did not realize how complex, like a single mutation can cause so many different variations in the blood cells themselves. So it's tricky to do, but that's what we're starting to do to try to better understand that. It's fun, scratches my physics itch because I'm a physical, like looking into how all those things influence our measured blood flow. It's a good question.
So that was a very interesting presentation. Thank you. I have a question about the models that you are using to describe like lead propagation in tissue. So you can use like the simple homogeneous semi-infinite medium, or you can use like layer models. And in case you want to the more complex layer models, you have like more parameters to determine.
Yeah.
So do you need to increase the number of source detector distances or the number of wavelengths or things
Yeah,
like that?
that's a really good question. So I think maybe even in that paper that I cited, no, it wasn't that one, but my grad student did some work. You have to have at least 2 separations to get a unique solution if you do a multi-layer model.
Mhm.
And then honestly, like the easiest way, all these new hardware advances are great, but they all have little drawbacks. The easiest way to improve depth penetration would just be if we could use a more complex model.
Mhm. Yeah.
But I can tell you it is not that easy, right?
Yeah.
Like it also has its own can of worms. So yeah, you run into problems with uniqueness, and then just measuring the thickness of the layers. Like even if you have an anatomical image of somebody's head, you have no idea how like lumpy, bumpy your scalp and skull is.
Mhm.
So what distance do you measure? You know,
Yeah.
that
Yeah.
kind of stuff. And a millimeter error in your thickness can cause like 50% errors in your estimation of brain blood flow. So it's tricky.
Yeah. And also maybe the number of layers that you are using, because you can do 2, 3, but then how many real layers you
Exactly,
have?
yeah.
Yeah.
So it becomes much
Mhm.
more complicated.
Yeah.
We have found the 3-layer model fits brain data better. And yeah.
And one question about the technology, let's say, is this technology being already like available as commercial
Commercially,
devices,
so
products?
their ISS Incorporated sells a DCS component with one of their near systems. It's called the MetaOx. So researchers can buy that. That's not a clinically available tool. It costs like an exorbitant amount. You could build it for much cheaper. I hope I conveyed in my slide how simple it is to build a DCS box. And then, and actually, I don't think it's a great system because it's a lower power laser. So, but then there's also a company called, what's Target's company called? I can't remember what it's called off the top of my head, but there's a company out of Spain who has a system as well that they've commercialized again for research use.
Mhm.
I think that one only has 4 channels for detection, so the SNR is a little worse. I don't know. I'm surprised there aren't more people selling devices. I think with time there
Mhm.
will be. One of the challenges is like certainly FDA clearance will be trickier because we use higher power lasers. So I like SCOS because there's a company called Open Water that it's not the company Open Water. It's that has figured out a way to pulse the laser such that like it's what a class 0 laser. So I think that's got a lot of potential. That'll make commercialization a lot easier, but that has its own drawbacks too. So one way or another, we'll get there though. Not commercialization doesn't have its drawbacks, but the SCOS system that they made has its own drawbacks.
On that note, why use DCS over SCOS? I know like DCS needs a higher frame rate, so maybe more expensive.
So
Camera?
SCOS can't do, okay, shouldn't say that. It is harder to be quantitative with the blood flow index with SCOS. So you have to do multi-exposure times, and then that makes it challenging to estimate the coherence factor beta because you have to assume that beta is the same on your different exposure times, which it inherently is not because of the pulsatile flow in the, you have to assume that flow is the same to estimate beta at your multiple exposure times. And so it's, I think it's a great tool to estimate blood flow pulsatility, although there's I'm not even sure the paper is out yet or if I just saw it on medRxiv, but they compared the pulsatile blood flow waveforms that they got with SCOS to that of DCS and maybe something else, and the shapes were a little blunted too. So it makes me wonder, because they're doing this uh, it's effectively a temporal averaging when they do their exposure, it makes me wonder if their depth penetration is shallower than they think it is. I'm not, I don't know. It's still early days in the SCOS community. I'm also not a SCOS person, although we've built a SCOS system in our lab. So probably if somebody from the SCOS world came and talked to you, they'd be like, oh yeah, it works and everything's good. So, so take what I say with a grain of salt. You guys had good questions. I'm impressed that you're so engaged. My brain would be so saturated after a week of intense talks.
I think with that, let's thank Erin. Thank you for the Well, now that- as part of the time, Well,